Good morning, everyone. Thank you very much for the introduction. So, I'm Gianmarco Gabrieli from IBM Research Europe, located in Zurich, and also a PhD student at the University of Rome Tor Vergata. And today I'd like to share with you basically the work that we have done with our research prototype, Hypertaste. In particular, I will focus on unveiling the cross-sensitive response of our sensor array for a specific use case, which is the quantification of ions in drinking water. So I will basically recap the concepts related to our sensor array, and I will leverage AI-assisted chemical sensing. And then I will focus more really on unveiling the array cross-sensitivity and show a few approaches to determine feature importance, including Shapley values to optimize the sensor array design for a specific use case. So Hypertaste is a miniaturized and portable electronic tongue that we use for liquid fingerprinting, and is based on an array of cross-sensitive polymeric sensors that from which we record potentiometric signal through an hardware device. And basically the raw measurement as well as the result of the analysis are displayed on a mobile platform. And the interpretation of the signal is done by AI and machine learning models and is deployed on an edge device such as smartphone. And the good thing of the technology is that being based on non-selective sensors, so these are just highly sensitive sensors, can be reconfigured for different use cases. And that's why it's interesting for the IoT space and applications. So the sensor preparation usually requires the electrodeposition of conductive polymers on our sensor array. We have different electropolymerization techniques, and we deposit polymers such as PDOT, polypyrrole, polyaniline, or PABA with different doping agents in order to enhance the cross-sensitivity of the sensor array. And we have 8 electrodes on one side and 8 on the other side. And from these 16 polymers, we record 15 differential voltages that we measure during training of the e-tongue with different training liquids. So the acquisition is performed through our automated setup based on a rotating platform that allows us to reproduce the measurement methodology. So the methodology consists in dipping the sensor for 120 seconds in a reference solution to condition the sensor, and then goes to a test solution for 60 seconds. And basically the acquisition is repeated for more liquids in order to train the e-tongue for recognition of new unknown samples. So during this, during the acquisition, basically we record 15 differential voltages, as I said, and from each voltage and each test, we extract 5 handcrafted features, so that are related to, the point, yes. So are related to both the final equilibrium potential as well as the transient response when we dip the sensor from the reference liquid to the test solution. And basically what we do is having 15 voltages and 5 features, we end up with a 75 feature input space. And from each feature, we can determine the sensitivity to a certain compound, for example. So in order to do that, we test the array with different concentration of analytes, and we can determine the sensitivity as the slope of the feature variation with respect to the concentration of that compounds. And we have seen indeed that there was sensitivity of the sensor array to both inorganic species, yes, as well as to organic molecules like acetic, lactic, and citric acid in a sensitivity range that is compatible with the beverages that we find in commercial products. So we then were able to apply this technology platform for different use cases. We have tested, for example, the recognition of the presence of defects induced in gold standard samples within production line of soft beverages. We estimated the multi-ion concentration in products in which we wanted to test the if some of the ions were exceeding the limit of the concentration range. We applied the sensor array for a reconstruction of sensory profile associated to coffees, as well as monitoring of water and oceanic water with an automated setup with microfluidic connection in order to determine the carbonate equilibrium in water. So now what's the actual challenge here is, okay, we applied the sensor for these different use cases, but the question is, how can we interpret this response of the sensor array, and how is it possible to optimize the sensor array design? So that's the motivation here. And in order to understand that, we started from a really simple case, which is the determination of 3 different ions, like calcium, magnesium, and sodium in mineral water, so in different locations in Switzerland. And then we trained the sensor array with 28 training liquids based on spiking of different salts to achieve a concentration range, again, which is known to be found in drinking water. Then from this data set, we applied 4 different models, a random forest of extra trees, a Gaussian process regressor, a simple architecture as for artificial neural network, and multitask learning with joint feature selection. And we observed high capabilities of the sensor array to determine the concentration of the 3 ions. Here I show the result for the ANN, both in the cross-validation with leave one solution out, as well as in the test set for the waters obtained in Switzerland. So again, the question is, how is it possible that without any calcium or magnesium or sodium selective sensor, we got good results? So which sensors actually contribute the most to the prediction and why? So to answer that, we started really from just the chemical experiment. This is how one will do with a selective sensor array, which is testing single ion solutions and evaluate the sensitivity of each feature. Here, there are the 75 features that I mentioned before, and each has a certain sensitivity to the different ions. And you see that the sensitivity profile for calcium and magnesium is quite similar, and it differs from the one that we have instead for sodium. And this is expected due to the different nature of these ions, as sodium is a monovalent ion, and also the dimension is small compared to the other 2. And therefore, we see that there is high sensitivity for some features and some signals, and some others are less sensitive. Then we try to instead evaluate the sensitivity in mixtures. So we prepared an orthogonal experimental design with 36 mixtures with a random variation of concentration of the 3 ions. And we evaluated the sensitivity of the array. And we see that indeed for calcium, there is quite a quenching of the sensitivity compared to a reduced sensitivity in magnesium, and almost immutable sensitivity instead for sodium. Again, a proof that the sodium prediction is not affected by the other 2. At least this is what we see from the chemical experiment. So if we plot the 36 mixtures on a principal component space, so here is the same principal component analysis, just changing the color depending on the concentration in those mixtures of calcium, magnesium, and sodium. So if we take the average, we actually see that the trajectory followed by the test for sodium is perpendicular, orthogonal, to the trajectory followed by calcium and magnesium. This means, again, that sodium prediction is independent from the other 2, while the other 2 are quite correlated to each other. Although we can still reconstruct the trajectory for magnesium, a little bit less for calcium. So this is the way in which we try to understand the array cross sensitivity, and then we went a step further by evaluating the importance of features from the model that we trained. So as I said, we have an extra 3 model in place, and we estimated the feature importance with the out-of-bag observation and prediction error on that. Then we have the automatic relevance determination approach in the covariance function of the GPR, and the connection weight approach for ANN, and the weights that we obtained during training for the multitask learning. Then on top of these 4 independent methods, we try to apply a common method that we have seen yesterday during the session, which is Shapley. So Shapley values, as my colleague yesterday from Infineon said, is an approach that can be applied to any of the models that I just showed, and is based on the collisional game theory principle. So what we do is evaluate the performance performance of all models trained with that particular feature with respect to the models created with all the possible coalitions made without that feature. And we wanted to basically compare the performances of these two approaches. So then, if we go back again to our sensitivity studies, and we plot the average feature importance from the models, we see again that there is a high correlation of the sensitivity in the single ion and mixed ion solution and the feature importance for sodium. And again, this is expected or like confirms the unique response of the sensor array to this ion. While for the other two ions, the situation is quite messy, right? So it's difficult to create a relation between the feature importance and the sensitivity in single ion solution. And this is because, again, there is a competitive effect between calcium and magnesium. And while in magnesium, we had a really high peak that outperforms the other more than a factor of 2, for calcium, there is more confusion in determining which feature contribute the most. And this is expected again, because as we have seen from the sensitivity studies, the trajectory for calcium was quite reduced, quite small. Therefore, there is a need of the sensor array to employ many more features, you see many more distributed peaks in order to contribute to the regression of that ion. And last point is the Shapley values that we applied. And you see here that we superimpose over the feature importance methods. And we see that there is really high correlation, as stated by the ICC parameter, of the feature importance methods obtained from independent studies with Shapley values. And this for us was a really interesting finding, because this means that for all the applications for which we will use our sensor array, we can integrate on our mobile platform a unique approach, such as Shapley values, to understand which features will contribute the most to that prediction. And therefore, we will inform the sensor array design for specific use cases. So as I said here, we identified the need of having new approaches to identify the importance of sensors for low selective sensor arrays. We have seen that the mixture models help us in unveiling the cross-sensitive response of the sensor array. But ultimately, we will need explainable models, such as the feature important methods or Shapley values, in order to understand exactly which of the polymers or features are the most important. And this is ultimately the goal, to be included for all the sensor approaches that employ data-driven techniques. So with this, I would like to conclude and